In today's video, I will walk you through how to take a math formula you understand and implement it in a language you know. If you don't understand the math formula or you have a problem reading math, you can take a look at my previous video on the subject. The formula we'll be coding is the Adam optimizer, and we will code it in Python. So let's start by taking a quick look at the formula. Okay, so like I said, the algorithm that we're going to try to implement is Adam. We're going to take a look at the formula quickly and try to make sense of it. I already made a video where I deciphered it from not knowing what it was. In this video, I'm just going to go quickly about what each of the parameters mean, and then we're going to implement it using a Jupyter Notebook. So the algorithm look like this. This is like a stochastic gradient descent or gradient descent based formula. So you have your parameter, you have your new value for the parameter, and then you have your update by where do you want to move into this cost plane. So this is easy. This is the parameter, and this is the new parameter. So this is what we're trying to calculate. Then we have this. This is the learning rate. Usually for Adam, it will be set to a particular value, and not really. There's no tweaking of the value that you need to do, because the whole point of Adam is to automatically update the learning rate. That's the idea. Here, this epsilon is just for numerical stability. So we're left with this value and this value over here. Yeah, that's it. So over here we have these values that are there. What actually is important is this bottom part is only for the bias correction. Don't really know, like let's assume that we understand what this formula is doing, and you just need to use this number, so this one and this one, so b1 and b2, and do exponent something t where you're at 1 minus that. So that's the idea. And over here, this mt and vt are those two values which have the form of a running mean. So that's pretty much it. So we're weighting the past values with the new we're weighting the past value with the new gradient values over here. So this gt, this is the gradient, so it's actually 1 minus b1 times the current gradient. We call it the first moment, and this 1 minus b2 g, the gradient at t, exponent 2, this is called the second moment. But since we're using stochastic gradient descent, it's just like one value, so talking about moment is yeah, whatever. So that's what we have. We have this guy, and this guy. So let's try to implement that thing. So here we are. This is the notebook that we're gonna use. If you look, I've already implemented a bunch of them, so I kind of know how to do that thing, but I never actually implemented Adam, so this is what we're going to do right now. So the first thing you do when you're trying to implement an algorithm, not an algorithm, if you try to implement a formula from scratch, is what are my use cases, and you try to constrain a bit the problem. I try to keep it simple at the beginning, and then try to make it more general and more complicated. So in this case, I'm gonna set the problem so that I always have a linear function, right? So I don't have not even a linear function, a line. I always have a line, never something that is greater than that. In complexity, I don't have something non-linear, just a linear function. It doesn't really matter for the formula, but it's just a setup around it that will constrain it, and then you can generalize the setup. So don't try to have too many problems in your head. The problem that we're trying to solve here is to make a function that will do the formula, right? So this is the formula that we're trying to optimize in this case. We're going to use a squared error over here, and we're also going to have some test cases. The test cases are down here. They are super simple. Here we're trying to make sure that the algorithm can find the best fit for a line with intercept 0 and slope of 1. We also have intercept 0 and slope of 2, and then intercept 1 and slope of 2. So that's the setup, and you have to have this kind of testing going on. Otherwise, how do you know that you didn't make some numerical mistake? So that's what you have to do. This is I think I will say this is less than the bare minimum. You should have an extensive test cases, but here I just want to show you the process I go through to create that thing. So you can read over here if you want, but this is I'm just creating a model called line, and with 2 parameters, and this is my evaluate function. So it's just like running the line. I have my derivative for the gradient, right? Because I need that in the formula. If you remember over here, I need these things, right? So I got that, and I need one of them. I need one of them for the parameter for each parameter. So this is for W0 and this is for W1. That's it, right? I have some helper function to help me do the stochastic part of stochastic gradient descent. So I'm just gonna get one value, and that's pretty much it. Everything else is not important. This is gradient descent, momentum at the grad, Hermes prop at the delta, and we want to make Adam version of this. So you should always start with your input output, right? So name the thing properly. This is what we have, right? And we're gonna try to think a bit about what this this value should have. So Adam, this is what, so this is that build upon the delta and RMS prop, right? Because this is like, it's just one more running average that you add over the whole thing. So this is what you have. At the end of this whole thing, we should not return anything. We should just update the model, right? If you look at the setup here, I'm creating a model called line, and then I'm gonna, in the previous things, I'm giving the model, and then I'm expecting this to modify this model. So it kind of has some state effect. So I'm not going to return a new model that is optimized. I'm going to actually work on the same model. It might be good or might not be. But to simplify the problem, I'm thinking an input output. I'm giving a model, right? Do whatever you have to do with it, and change this model so that it's fitted. That's what I want. So this is what I give. So this is my input. Do I need to? No, good. So I'm gonna give a model. So this is the model we want to optimize the parameter on, right? So if you have only the model, will this thing work? No, right? What do you need to make the update work? At the bare minimum, you need some data, right? Those algorithm, it's not explicit in the formula if you just look at it, but if you understood it, you know that these gradients, they don't come from nothing, right? They come from applying the function, right? And getting the derivative of them, and then trying to find the gradient of each of the parameter using the partial derivative. Then this is the part where we need data, and this is the stochastic part of this gradient descent based algorithm. So we need data. So we need a bunch of x and a bunch of y's, right? So if you look at the line over here, if you look at the line, you have an x, right? This is my y. By giving an x with the new parameter, how far I am from the true value, right? So you need this kind of label, and you need this kind of input parameter, and those we're going to be tweaking them until we're able to have something that is always right, or kind of right? Because here we have it's a regression. So I need a bunch of x and a bunch of y. So here I'm calling them xx and ys because this is what I've been calling them every time. And this is my the feature of my dataset. So x are the feature and y are the continuous value. So this is the target. That's it. So if I have only this, if I have only the model, I know what my output is this model change. So I have the model, I have a bunch of data points, and they know it's aligned. So what else do I need? This is where you look at the formula, right? And you start with the obvious one. You have this guy, right? An epsilon. So this, we already know the value of it. It's going to be 10 to the exponent minus 8, right? So this needs to be there somehow, and it's a good thing to put it over here. So you put it like this, maybe like 0, 0, 0, 0, 0, whatever, right? So it's this really small number. So we have this, and we know this is for numerical stability. Variable numerical. Okay, so we got that. What else do we got? We got those two, right? So as soon as you see a number, if you're looking at the research paper or whatever, if you see a number over here, and the author says, we propose those default value, go with these, but make sure that it's fitting the same setup as the author. So the other over here, they were looking at deep learning kind of feature space. Here we're looking at line. So those value might not be good for our setup, but always start with the proposed default value, and after that you can tweak it to your problem if you need to. But these you should it's like a gift for you, so you already know what it is. So we have B1. So I'm gonna keep actually the same methodology. So B1 I don't like, well actually yeah, just keep it like this, and B1 is 0.9, so 0.9, and we have B2 which is 0.999. okay, so how did they find this number? Usually they tried a bunch of stuff, right? They tried a bunch of stuff, they did some test cases, and then they saw what number were giving the best performance. And usually this takes a lot of time. This is the part where they don't say it in the paper, and they just say we propose these values, but actually they spend like most likely a solid month just trying to figure these out. Good, so we have this one, this one, and this one, and then this is where you go into the formula and try to pinpoint what's left. These you don't need, right? This is abstracted by my model class over here. So in the model, if you look over here, I have self.w0, self.w1. There's a better way to do this. You can have an array if you want to make this a more instead of having a line, you can have a linear model. But here, just for the purpose of clarity, we have w0 and w1. Those are embedded inside my model. So just make sure that whatever abstraction you're creating makes sense for your use case. So here B1, sorry, I'm creating documentation along with this. This is the first decaying average. This is the second one. Create proposed. Okay. Okay. So I tend to like to make more documentation that really needed, because I'm working mostly on like a research project where nobody knows what the actual output will be. So I prefer to really document my stuff correctly, because I know at some point I'm gonna come back here and look at this B1 and say where this came from. So if I can just read the doc string, it's easier for me than if I have to dig back on my node, find whatever source I got. So that's just me. Good. So these guys over here, do we need them as parameter? No, we don't, right? If you look over here, they come from within the problem formulation. Same thing at GT, they come from within. It's not like you give them and then it will trickle down. You could maybe give the initialization of the very first MT and the very first VT, but you don't need to. You can hard code it directly in the formula if you know really what you're doing. I think the only thing that's left, and those ones are a byproduct of MT and VT, so it's a byproduct of these. So the only thing that's left is learning rate, which is kind of funny, because you're not supposed. This is the whole point of this, is to not have a learning rate. But I'm gonna put it here, 0.1. So learning rate. So if you like, usually in stochastic gradient descent, if you have small learning rate, you're gonna make some super tiny steps in the cost plane. If you have a big learning rate, you're gonna make some bigger step, but you might just diverge completely. The whole point of Adam and AdaGrad and RMS prop is to not think about the initialization of the learning rate. You want it to be adapted to whatever is happening during the analysis. Okay, good, perfect. So so this default is 0. Right, good. So I have my input figured out. I know what's gonna happen. I just need to give it those input, and it should fix my model. Doesn't matter how, right? So this is where I would technically just go over here, say Adam, create my model again, which is gonna be a line, print my setup, give my model, my XX, YS, and print the model final thing. Good, so name line is not defined because we didn't run that. So here we're trying to do intercept 0 and slope of 1. It should do absolutely nothing, right? So iteration, whatever, good, blah, blah, blah. And Adam actually didn't even run. Oops, sorry. We're not even at the right spot. Here, Adam, this is my initialization for my model, and it's totally off, right? But this is perfect. So it's kind of like a test-driven development kind of methodology, but without much test. So that's it. If you look, this is stochastic gradient descent, right? So every time I'm gonna run the thing, I'm gonna make one update, right? How many updates do I need, right? In the Adam, it doesn't say when it should stop. You could technically make some rule where if there's no improvement in the error rate as you go from step to step, you stop and you return. I feel that this is giving a bit too much power to the algorithm, what I would do is give another variable that says, I want this to run for that much time, right? And that's it. So I want to have a max number of iteration in my algorithm. So this will run for X number of steps. And I'm gonna give it, I'm gonna put it over here, max iteration. Let's say 1000 steps. Good. At this point, we have nothing. We just have a good set of input, a good set of output. But this remove some kind of a mental workload. You don't have to worry about like what goes into the system. Now you just need to figure out what's inside the system, and you know that it's like a bounded problem because you have your input and you know what you have to output. I like to think about it like if you were in the kitchen and you want to do some recipe, you could just start right away and try to figure out on your own. But at some point you might realize that you need to go to the grocery because you don't have X or Y. So the first step is to figure out, do you have everything that you need? Yes or no. If yes, good. If no, go fetch it, right? So in the term go fetch it here is go back to the formula and fetch it and put it there. And do you really know what the output will be? Are you going to do a cake or whatever? So here we know exactly this needs to be optimized. Perfect. So this is where you should actually start the stuff, right? We're gonna have to update each of the parameter over here. So this will need to happen somewhere, right? But before this happen, this need to happen. And before this happen, this thing need to happen, right? So we have this thing called m of whatever. We need to keep in memory the previous one because this will be used for the new one, and the new one will become the previous one, right? So we need to keep a m. I'm gonna call it, I'm gonna call it m. So here we're gonna have some variable initialization. So we're gonna have m. I'm gonna set them to 0 at the beginning, and we have v. Right, so both of them are going to be set to 0, and these will be updated continuously. So the goal of this part is to find m, use the previous m to find the new m, replace it, use it over here to find this thing, and then use that over there, right? So here we're gonna call these core m, so the corrected version of m, right? And this, do we need to keep that actually? No, we don't. We don't need to keep that ever. So these could be like, we don't need to define them over here. The m corrected could be directly inside, and we don't have to worry about it. That's one thing. And then we're gonna have the gradient. Do we need to keep the gradient in mind as we go through it? No, we just need to calculate. That's it. Once we calculate the gradient, the next iteration doesn't matter. So here I'm thinking about iteration. So that's it. We don't need to keep that. Perfect. Good. So here that will work if we have only one parameter, right? But remember here we're gonna have like some amount of parameter. Here we're gonna have 2, so we have to have the 2 initialization. How do I know that? Right. If you look over here, you have this gradient, but the gradient is for each of the parameter. So you might have like 10 gradients, each for one partial derivative. So you're gonna have to have 10 of these because these will depend on g, his own g. So it should be a vector. Here we're trying to minimize our uses of external libraries, so we're going to do it like the slow way, just so that you can understand it properly, and then after that you could use some linear algebra to simplify this the whole formula thing, but here we're going to make it very explicit. So here we have 2 parameters. So I'm going to say it here. So 2 m for each parameter, right? So that's the idea. So we're gonna have this one. So now we could calculate technically the new m every time, and we just need to get the gradient. Good. So how we're actually gonna get the gradient over here? How can we get the gradient? So let's take a look at this. If we do dx w0 and we give it the x and a y, we're going to get the partial derivative, which is the gradient. And dx w1 on the model, we're going to give the x and y and going to give us the gradient. So this is our setup. So we need to have an x and a y somehow over here, right? So let's kind of go and say it. So let's say model.dx w0. We're going to give it an x and a y, and here that will be our gw0, and our gw1 will be model.dx w1 x y. Where those x and y come from? They come from here actually, right? Or x's and y's. Which one should we choose? This is where you have to really make sure that you understood the formula before you try to implement it. If you don't understand the formula, there's no point in trying to fiddle around at this and just try to hack your way through it. It won't work. You're gonna get lost and your code will be a mess. So here we know that Adam worked in a stochastic gradient descent way, so we need to stochastically sample that thing, right? Hopefully we thought about it and we did some setup before, so we can use this thing. So you give it an x and a y, and what you will do, it will like permute the thing and take the first thing, so it will shuffle it and give you 2 of them. That's what we want. We want to sample with replacement, and we just want to take 1 of them. So wait. Okay, good. So here we have this, and we're gonna have x, y. Ta-da, right? So we have m, v, we have x, y, we have our gradient. What else are we missing as a gradient? So now we can technically calculate these, mt and vt, right? So let's calculate it, right? If you look at this, something is off. Like it cannot be just like one go like this. But you see, I usually do the simplification of the problem. So let's say we try only to do 1 iteration, and then you extrapolate once you did 1 iteration, you extrapolate to the max number of iteration over here. So here, calculate the gradient. That's the whole purpose of having x and y, is to calculate gradient. Once we have gradient, we don't really care about x and y anymore. So we're trying to implement this. So this will be this will actually be m0 and our m1. We're going to fix them. So we're gonna have that formula, b1 of the previous one. So b1 times m0, right? This is what we want. Plus what was it? 1 minus b1. 1 minus b1 times the gradient w0, right? There we go. And then we want to have same thing for m1. So 1 minus b1 times gw0. So we got our m properly. This gw0 kind of limit ourselves, because we could just make a for loop over here. So we're actually gonna do I'm gonna make that like this. So G will be something with like that. So that will be our initialization. So this is the 2 gradient, right? So we're gonna do this, G0, G1, right? This limits us a bit, but this is the specification of the model. So what we could do then is just to have, can do a list comprehension. So I'm trying to make a list comprehension over here for mi gi in zip mt. So that should technically work. This mi one blah 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 plus gi over here will feed each of the index over here, and the m1 and mi and gi will come from m and g over here. So m and j over here. So those will be kind of going together. So I can make a one liner over here, and then same thing for the v, except we have v2, and this needs to be exponent 2. So v equal b2 times vi plus 1 minus b2 times g I times gi for vi gi in zip v and j. Is that it? Should be good. Yes. So we have our m, our m and our v. We're good with that. So this is our new m and our new v, and now we can have our bias corrected m and our bias corrected v. So here, update the m and v parameter, right? So we're kind of done with that part. We don't need to look at it anymore. We just need to focus on these two now, and we can kind of abstract and make sure that put in our mind that m and v will always be fine, right? Because we know that the g will always be fine because we can calculate the gradient properly. So we can think about something else. So here, bias correction for m and v, right? So we have to bias corrected them. So I'm going to call it m core, and we need to bias correct all of them with the same thing. So this is actually going to be another a list comprehension. I'm going to do the same thing just to see the abstraction here. So then let's say m core at 0 we're going to be what? It will be m at 0 divided by 1 minus b1 exponent something. So exponent our step, how far are we in the thing, right? So sorry, this could be that. Let's put it like that just to be sure. So here this will need to be exponent t, that thing. Yeah, need to be exponent t. So we somehow need to take keep track of the steps. So this is the time steps, right? If we don't keep track of the time steps, that won't happen. We won't be able to do that. So that's it. So here, if we do a list comprehension instead, we can have m divided by 1 minus, well, no, not that, mi divided by 1 minus b1 t. We could calculate b1t before and just like not having to calculate every time. But that doesn't matter really in this case. That's it. And the same thing for v. Then we have v core equal vi divided by 1 minus b2. Is that the same thing? Yes, same thing. For vi in v. Good. So this is the bias correction. That's it. We don't actually need those. We don't need to initialize them. We're good to go with that. Perfect. So we bias corrected our stuff. We're done with this. We don't need to ever look at it again. So the only thing we need to look at is this, right? So we have this, and we have that and that. So it's not even complicated to update the parameter. Here, this is where because of how it's set up, we're gonna have to update this one and have to update this one. So that will be a bit clunky, but that's how it is. So W0 is model at W0 plus the update, right? And the update we want is actually we can do it like they're doing it. So minus that blob of things. So learning rate, right? You remember we define it over here. Learning rate divided by that thing times this. So we can say something like learning rate times m core at 0 divided by that thing over here. So the square root, here we're going to use numpy, square root of v core 0 plus epsilon. We're good with that? I think so. Just to keep consistent, I'm going to take this and just put it over here. Put it here. Yeah. So just to keep everything consistent. So n divided by this times that, doesn't really matter, but just for myself. And same thing for the other one. So w1 equal model w1 minus this whole thing for the other part. So v1 equal 1. That's it. And there we go. So here we saw one possible problem. Well, no, one possible optimization. Here we could use a list comprehension if we didn't have those things. And better than that, we could use some linear algebra to speed up the calculation of all of these things. But this is how the model is set up. So let's not worry too much about it, but we can take a note mentally that there's an optimization here. Last thing we want to do is do t equal t plus 1, so that the next round we're going to be able to calculate the b over here, this thing properly. So we need to do that every time. So if we go through it again, right, we initialize that stuff. This is before, and this is what needs to happen every time. Right? This needs to be repeated every time. Every time we're going to sample, right? Calculate some gradient. That's fine. Calculate, update the m and the v parameter. So this is good. And then bias correct the stuff using the t, update the parameter, then have these this update of the timestamp, and then reiterate. That's what we want to do. We want to go around like this. So how long do we want to go around this? We want to do that for max iteration, right? So for in range max iteration. Actually, I'm gonna keep I over here so that every time we're gonna do that loop, we're gonna actually update the model. So at the end, the model should be fine, right? And that's it. You see, I've did it only for one timestamp, and then I just need to make a for loop, and then that's it. This is for X timestamp. I'm just gonna keep that so that we can print it out. And that should be good to go. and we're going to print the model so that we can see the parameters. Most likely messed up something, so let's actually let's comment this whole thing out for now. I hate to do it like that, but okay. So let's, oh, I messed up. Okay, let's run that. So Adam, we got some non-initialization. What the hell? Oh shit, yeah, okay, now I get it. I think this is the issue. Okay, so let's run it again. Good, perfect. So that was, sorry for the wait. So I figured out what the mistake was. I had bracket over here. So if I just write it like this, it will be m1 divided by this minus that thing that keeps on getting bigger. So you're gonna get a negative value, which will trickle down into the square root over here. So you're gonna have negative square root. So you're gonna have an n. So we're gonna have an n over here. So this is why we got this. Perfect. So I think we can technically go with T0. No, we cannot. So we need to start at T1. Yeah. Perfect. So y blah 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 blah. That's great. I don't need to print it every time though. Why is it printing it every time? Okay, no, it's not printing every time. So the thing goes down and we get it. That's it. So if you look, we're trying to do intercept 0 and slope of 1, and this is intercept 0 and this is slope of 1. So that thing worked. The whole thing worked. So let's try this again with the other setup. This should not be marked down. Okay, so let's go with that. And this should be intercept of 0, slope of 2. It's converging to this really well, actually, good. And let's try the last one. So intercept of 1, slope of 2. Okay. Wow, good, perfect. So this is working perfectly well. I've tested with a few test cases, but we should test it with more. But that's the gist of it. Like you kind of make sure that you have your test cases properly set up so that you catch any problem like we saw before, and you just go slowly when you implement it, right? So like you said, what I did, I started with some variable actually started with the input output, then I went to variable initialization, and then I went step by step following the formulation from the top up to the bottom. And once I got for one iteration, this is where I went for the other iteration. It depends for your problem. Sometimes you don't have any iteration, you have like one shot thing. Sometimes you have a recursive thing. But the idea is that you always have to go back and you have to make sure that you understood the formula before you implement it. Alright, so that's it for today's video. I hope this was useful. If you have comments or questions, you can leave them in the comment section. And like always, have a great week.